Here's a second related rates example. I'm going to focus just on the mathematical heart of it for this one, and then in other examples we'll go back to more applied problems where we have to think more about the context and some of the subtleties. So here's a fairly artificial problem, but it's in the same spirit as the algebra that we get in a fair number of real examples. So we know that three quantities related by z to the fourth equals x cubed plus 2y squared. Big thing right at the start is that there's three quantities, and so if I want to know, for example, the rate of change of one, I'm going to have to know the rate of change of the other two. That's two rates of change being input, or have some other auxiliary equation. But there's no other auxiliary equation here. We just have what I would call the master equation. Okay, but we are given two rates of change. dx dt is known to be 5, dy dt is known to be -3. And the question is, how fast is z changing? And that's going to depend not only on how fast x and y are changing, but on exactly what those quantities are at a given moment. And this is often how you see it in books, especially in Stewart. They'll highlight the master equation, or there'll be some situation where you need to figure out the master equation. They'll give you the rates, and then it'll almost be an afterthought, the actual values of the quantities. And that's kind of actually helping you out because it's suggesting that these should be plugged in last, and that's really crucial because you don't want to plug in values before you differentiate, because otherwise nothing has a rate of change. So this is the heart of the method. We're going to differentiate the master equation using the chain rule. So derivative of something to the fourth is 4 times that thing cubed, but then times the derivative of what's inside. So again, even though it doesn't look like it, because we're differentiating with respect to t, z is really a function of t. It's a variable quantity that depends on time, so it's a function of t. So this is really a function inside of a function. Okay. Similarly here, this is going to be 3x squared times the rate of change of dx dt, plus 2 times 2 is 4, times y times the rate of change of y with respect to t. So there's our differentiated master equation. That's crucial. And now we can plug in almost everything. We know almost everything here that we want to know, that we need to know, and of course what we're trying to solve for is dz dt. So we know dx dt and dy dt, and now and only now we can actually also plug in the values and say, oh, we happen to know that at the instant that we want to find dz dt, we know the values of x and y. Okay, so let me just leave this alone for a second though, and that's going to be the one remaining subtlety, but very common. Okay, so this is going to be 3 times 2 squared is 12 times 5, and then plus, what's going to end up being minus, because 4 times 2 is that's 8, and then dy dt is -3. Don't forget those signs. So in a word problem, this would probably be something like y is decreasing, or something getting smaller, or going lower, or something like that. But here, it's just given as explicit sign. So -8 times 3. Okay, because that's the dy dt is minus, and that is 60 minus 24 is 36. Okay, so we want to solve for dz dt, and this is one additional thing that can be tricky for people. Well, what's z? They didn't give me z. Well, that's why I call this the master equation. You don't just use it once, you might need to go back to it multiple times. We know that always in this situation, no matter what x and y are, z is related to it by this equation. So certainly when x is 2 and y is 2, this is going to be true, and we're going to be able to find out what z is. Okay, so we go back to the master equation, and we get that z to the fourth, at this instant that we've been told to be interested in, that's 8, and then 2 times 2 squared is another 8, and I did contrive it so that it would be nice. Not really that realistic to contrive it that way. Ooh, a piece of paper. But z is going to be, and actually, come to think of it, there's really two answers. I forgot that this one, yeah, so really z, if we don't know what kind of sign this quantity has, z could be plus or minus 2. Let's just, to make it simple and get a definite answer, let's say we happen to know, and this is the kind of thing that you're going to know very often in a realistic problem, that some quantity is maybe a length or something like that. So this is something that might be some funky relationship between lengths in a geometric situation. Let's assume we know that z is greater than 0. So just to get a definite answer, z is going to be 2. And, okay, and that plugs back into here. Let me just cheat a little bit so I don't have to rewrite stuff. So that's going to be 4 times 8, that cube. And we're just going to get dz dt. Where do I want to put it? Yeah, I guess I'll erase some stuff after all. We're just going to get dz dt is 36 over 32, but I mean, we can just cancel that down to 9 over 8. It is 9 over 8. And we're done for this one.